Hi there. I'm David Reeder. I'm Director of Bryden Wood Technology, and I'm here today to talk about how automation is transforming construction, AnyLogic modeling of truss fabrication. So the specific project I'm be talking about today is called FASTtruss, which is a collaboration between Tata Steel, Bryden Wood Technology, and the AMRC, so the Advanced Manufacturing Research Center. So a bit of an agenda presentation structure. So I'm going to talk a bit about the project background, the methodology, inputs and data, results and findings, and then a bit of a summary of the findings and where we could go in the future. So first, I'll give you a bit of a background and introduction to the FASTtruss project. FASTtruss project is an Innovate UK project. So it's developing a design for manufacture and assembly, so DFMA solution, off-site manufacture of steel tube lattice trusses. So a lattice truss, it looks a bit like the image in the top right. So you have longer sections and shorter bracing sections, which form structural systems of lots of large span buildings. So these lattice trusses are often bespoke. They're manufactured with intensive labor inputs, manual handling of materials, and they're quite limited in repeatability and therefore scalability, which is quite similar to a lot of the components and processes in the construction industry. So FASTtruss is a system of standardized truss systems. So this is designed for mass customization and the scalability for a wide range of applications. But what this means is that fabrication and assembly of these products can be done in off-site factories with higher levels of automation than you typically find in construction, including things like robotic cells. And what it means also is that the storage, shipping, and on-site installation is faster, it's more efficient, with other benefits such as reduced working at height, so it improves things like safety. So talking a bit about the kind of application for this system, where it sits in the market. So there are a few different types of systems already out there. Things like you'll see on the left, which are, say, a portal frame or a traditional truss system, and they cover off, varying spans of the market. FASTtruss sits somewhere kind of over the portal frame area, and it covers a bit of a gap in the market. So it's kind of showing that there is a gap for this type of system. It covers a wide span of buildings, and actually, there is a lot of the market that can be covered with products such as this. As I previously mentioned, this is a collaboration between Tata Steel. So you wouldn't probably know them, but global steel producer, but with lots of other projects such as this. Bryden Wood, so it's a global multidisciplinary construction design consultancy, and the University of Sheffield and Advanced Manufacturing Research Center, which do a lot of this research with manufacturing collaborators. So talk a bit about why FASTtruss is important and how automation is kind of transforming this industry. So construction industry productivity, it's had really little improvement for decades, whereas other sectors have had huge improvements in efficiencies. It's typically slow to adopt new processes and technologies, including simulation. And traditionally everything is focused on site, using bespoke elements, bespoke processes, bespoke workflows. And this means that there's kind of poor efficiency, inability to repeat and scale anything that happens. So projects like FASTtruss can leverage methods and efficiency gains from sectors like manufacturing. And this is really great. It can kind of transform the construction industry, and it can kind of change the way that projects and components are delivered. And as part of these digital workflows in the design, we believe that simulation can play kind of a vital role. So we want to be faster and smarter. So not the same thing, but better, or not just different and just as slow. So when we're talking about simulation, why we would choose AnyLogic. So basically, we, in collaboration with Tata Steel and the AMRC, we developed a simulation of the factory system. So we chose AnyLogic as the software and its built-in libraries provide a fast and flexible platform for development, which is really, really important for us, especially kind of the rapid building of simulations. So the simulation is built using knowledge from existing mathematical models, and this allowed further kind of dynamic analysis. And as we said before, we believe simulation is a core approach in the future of the construction industry. So traditionally, a lot of work is done, static models, static spreadsheets, Gantt charts, kind of tacit knowledge, intuition. And what we want to do is we want to change that, and we do believe that simulation and tools like AnyLogic can really build on that knowledge and become a core part of the tools in the future. So as part of that, where we want to make an impact and where we do make an impact in these projects is kind of trying to be at the early stage. So traditional projects or conventional approaches may, they don't test many options. They take a long time to do it. They don't iterate much. Then there's not a lot of feedback in the process. Whereas for our approach, or what we try to do with clients, which is kind of like the design to value methodology, is we create lots of options, help clients make choices, connect client requirements with resulting outcomes and solutions. And what we're trying to do is basically push simulation tools into this process, into an industry that's quite behind, and also push simulation further up that design flow, so that we're deploying it at much earlier stages than we otherwise might have. So the truss itself is kind of designed with an automated design workflow. We take inputs from clients and from the market, and there's a parametric design, structural optimization that designs this truss system, provides feedback. And as part of this workflow, we get outputs, models, designs, bill of materials, but part of that is an optimized model for manufacturing. So the actual factory that would fabricate these trusses off-site, and that's where we've used AnyLogic. So it starts with the demand, a product demand for the simulation. So the average daily demand for truss assemblies is shown below. I had to remove the numbers for sensitivity reasons, but it gives you the general idea that the market is kind of trending upwards, and there is perceived demand for these trusses. There's two main types of trusses. So there's rafters and transfer trusses, and you can see on the right hand side what that actually means. So you do have transfer trusses, the ones that run on the side of buildings, and the rafters are the ones that kind of make the pitched roof. And so it kind of shows what the system or what factory would actually have to achieve in terms of throughput. And that's kind of connected to what we do. So we can kind of show or demonstrate, whether one factory would be sufficient, whether it's two factories, or what portion of demand and how could a factory actually provide these trusses to market. So a bit about truss anatomy before I go on, using the image that I had before. So there's kind of three main elements to a truss. There's the long top and bottom bits, which are called chords. They're made from square hollow section steel, so essentially square steel tubes. Braces are the shorter diagonal elements, and they're made from the same materials. And then we have connections, which hold the different parts of the truss together, and they're made from plate steel. So the methodology that we use to approach this problem, the simulation structure was based on the latest process flow and facility layouts which had been developed by the design team. We decided to limit the model scope from raw material entry into the system to basically a general buffer at the end, which collected finished trusses after the final process step. So for this initial analysis, we wanted to focus just on the core processing elements. The inputs that we used for the model will probably be familiar to pretty much everyone here, I'd hope. But kind of things like the process flows, cycle times and timings, different truss types, dimensions, their parameters, production schedules, logistics, and other data. And then we had a set of outputs which had agreed with the project team and the clients. So things which would impact the viability of the factory and the process technology selection, etc. So things like accumulation sizing of buffers, processing stations, throughputs, and some indications of bottlenecks. So the general process flow was split into two streams. One of that is for plate steel, the connections line, and the other is for the square hollow section steel, so the steel tubes. Typically, the raw material comes in, it's cleaned, inspected, measured, marked, and then processed. So it might be cutting, drilling, and then it's welded together. It's inspected and tested again, and then it goes for painting and finishing. And the images on the right just give you an idea of the types of equipment that would be in this facility. So, you know, for these kind of proposed factories, it would be, you know, conveyors for large raw materials, or maybe robotic cells which do operations such as shot blasting or welding. So this is an approximate layout of the approximate layout of the factory. So you have raw material kind of inputs, cleaning, measuring, transferring, then three different processing streams for brace processing, plates processing, core processing, and then there's truss welding, which we had as robotic cells. There's truss buffers, cleaning and inspection, and then two large sections which are for painting. So these are priming painting, and then intumescent, which is fire-resistant painting. And these areas are actually more manual, and they are for finished trusses. So these trusses are, you know, many meters long. They're very large. They take up a lot of space. So this is one kind of focus of the model and of the project, because it means a lot in terms of resourcing and cost. And there were, you know, a few buffers that we looked at within the process, such as we basically call them A, B, and C, but they're within the truss welding, you know, within the inspections. So those are the areas that we recorded. So this is a bit on how we converted the simulation to AnyLogic. So we took that process flow. We mainly used the process modeling and material handling libraries, which was really useful because you can kind of just immediately use them. Conveyors we use for the main material transport routes. We could use conveyor stations to represent processing equipment, such as cutting, drilling, and inspections. We represented the welding stations and the welding streams using a series of nodes, and cranes and forklifts were used to move material between these conveyor systems, different buffers, you know, and processes like painting and storage. So lots and lots of cranes, but there are a couple of diagrams below and images below that show you just how, you know, we represented different processing streams within the model. So you had a sequential set of conveyor stations, you know, maybe for measuring, cleaning, transfer, and then on the right you've got the three different streams, and you know, you can represent the correct capacities and dimensions of all of these things quite easily, which is nice. And similarly, transferring the materials themselves to agents, we decided to simplify the problem a little bit, and rather than process every single raw material piece and raw material element, we decided that we would batch them together, which we agreed as a project team would be an okay representation for the way that the system would work in reality. So, you know, we would put all of the cords together, which would make up a single truss type, all of the braces, all of the plates. And so they were converted into, you know, individual batches with the correct parameters, the correct dimensions, and those were generated in the model based off the production schedule. And then they would be processed through the different streams, depending on what types they were. And eventually they would get welded together and become a truss agent or a truss shape within the model, which would then go through the rest of the processing steps. So some assumptions and data that we used, probably some typical things, but we did have to, as it was kind of quite an early stage initial model, we did have to make, you know, some quite high level assumptions, which is pretty typical, but they're things that we can share with the project teams and develop as we go along. So things like, you know, only considering core process timings, no constraints on availability of resourcing, no breakdowns, maintenance, we could operate 24/7. And then we removed the limits and constraints off of some of the different areas, so storage areas and painting bays and things like that. We didn't want to a bottleneck. We wanted to see, what the kind of maximum usage was there, what the accumulation was there. Just on the right to show roughly the kinds of data that we're using, so some of these provided by us, provided by partners. But again, shared between the project teams, kind of easy to share, and something you develop as you go along as part of that kind of iterative process. What also the simulation allowed us to do was easily test, lots of different scenarios. So we had a few different scenarios here, just to kind of, test the spread of outputs that we could get, the impacts of, certain inputs on the system. So things like transport times, whether we included them or excluding them. Obviously, totally excluding transport times is not going to be really realistic, but we wanted to kind of get a best case boundary output to see what impact it would have on the model. We had our process timing, so we sort of had our default static values, and then we also added in a plus or minus 20% triangular distribution on those certain scenarios, and then also for the production schedule. So depending on the actual lifting methodology of the final truss system, that changes the necessary production schedule in the factory, and we assumed that the production schedule in the factory would mimic the installation schedule that would be on site. So whether it was lifted from above or lifted from below, that gives you a different production schedule, and it changes the kind of variability and the number of campaigns essentially within the process. And we also had a different case study, so that was a smaller building and then two larger buildings. So I do have a video demo, I think, that I can play. Sorry, I'm just having a bit of a difficulty playing the video. Sorry, so just having a little bit of a difficulty playing the video there. But basically, this shows how the model itself was structured. So you can see kind of the similarities with the factory flow, which I showed before, and how this was represented kind of within the system. So we didn't have a huge user interface. We didn't have lots of different tabs and 3D views. We just wanted to get something done kind of rapidly that we could change and test. And so we had the process here, so the main kind of spatial layout on the top, and then so I had the main kind of spatial layout in the area on top, the logic layout below, and then different areas which were for the kind of interim outputs, functions, and then other outputs which we were saving to Excel and generating output files. Okay, so a bit on the results. So I guess again I've removed the numbers due to kind of sensitivity reasons, but essentially the main outcomes were that the kind of schedule and process time variations only made kind of very minor differences to the results. I mean, as expected, the most difference that was made to the results was the inclusion or exclusion of process times. And that means it's kind of something that we can focus on in a subsequent analysis. So one of the other findings or things, indications was how much of the demand could be fulfilled by one factory such as this. So it gave the stakeholders and also the project team an idea of how much of the demand could be, how much of the demand basically could be covered by one factory such as this with these assumptions at this early stage, and how many you might need in total to cover your predicted demand. So we also looked at the kind of sizing of hold, priming, and the secondary kind of fire-resistant intumescent painting areas. One thing that we did find out was that production schedule had a bit of a larger impact on the sizing of buffers and these holding areas, which is important for facility sizing, so resource requirements and cost. The most important kind of, I think, aspect for us was checking outputs against existing modeling that had been done and the results that had already been found. So it's basically, this is used for early costing and viability studies. And so what we found were there were closer matches for the model for the priming stations, but for the intumescent stations, the AnyLogic model suggested that there may be more bays should be allocated. And with these trusses being very large, that equates to a lot of factory space. It's in this case the painting processes are labor intensive. There's lots of kind of drying times and cranes that are used to move them around. So the more bays you have, the more equipment you need, the more space you need, the more people you need, the more complexity you have. So it's kind of good to find that out at an early stage, whether you are undersizing or oversizing things. So that was one interesting finding that we had. Generally, for the sizing of buffers, which I highlighted earlier, they were kind of more constrained by the other parts of the process, so there weren't really many variations in the results. But again, what it does is it does provide a little bit of either kind of confidence or indication that it's generally fairly sized. It's you're not orders of magnitude out, and yeah, it provides a little bit of confidence to stakeholders and project teams that you do have the right kinds of initial assumptions. So overall, a bit of a summary of the findings. So as I said, based on the initial assumptions and the data that we used, some area sizings and throughput figures were similar to what had been predicted by the project team, which provided a bit of confidence there. However, the simulation did indicate that other areas could require additional stations, additional space, or bays, such as painting, and therefore it highlighted areas for further investigation, areas for risk. And as I said, it makes a big difference, these early stages, for viability studies, technology options, and things like that. The variation in process timings only really resulted in slight output variations, so kind of indicated potential acceptable ranges when considering equipment and process options, and also just general, error. So again, at early stages, lots of things are quite unknown. You have to make assumptions, or you have to make guesses for the data inputs, and if you change them by plus or minus 20% or plus or minus 30%, and you're not really changing the system that much, that's fine. So it just gives, again, everyone a bit of leeway and confidence that they can make some of those changes. They can look at alternative technology options, and it doesn't really affect the end result that much. So the production schedules that we looked at, they only slightly affected throughput, had a larger impact on sizing of buffers, holding areas, quantity of painting stations, again, important for facility sizings, resource requirements, and cost. And exclusion of process timings, as expected, provided one of the largest difference in outputs, and highlighted a potential to kind of investigate different layouts, transport timings, transfer methods further. So what if you could reduce some or eliminate some? It means that you might be able to get some good throughput gains. And generally, kind of thinking of where next for this process. So you can kind of do, iterative reviews and updates of the input data and modeling results, which is great. And with tools like simulation and AnyLogic, that's really easy. So for this, it's just, and I'm sure for a lot of models, it's just a case of swapping out an input file, one input file for another, running, and then you can basically just generate a new set of outputs that you can then visualize. So what you can also do is do further investigation, maybe with the model that you already have, or with some minor tweaks. So again, looking at things like production schedules. So we've included, 2 or 3, but are there more? How does it change? Are there any production schedules that would really make a difference to your simulation? What's the most efficient production schedule? Things like different facility layouts. So, the current or the facility layout that we tested was just one of the initial ones, but there were alternatives which may be, down to the type of site that you want to fit on, whether there are any site constraints, testing, these kinds of things. Again, moving things around in the model is something you can do. Different automation and different technologies. So replacing, some of the stations that we had with different technologies, which means different timings, different processes. Again, something that's quite easily done and represented in the model. So the reliability, downtime, and working time constraints. So what we didn't include at the moment. Were things like maintenance, downtimes, if there are any working time constraints. Some of it is because the data is just simply not known at the moment, and it's something that we could, make assumptions on for the next phase. But again, these are things that are quite easy to implement in a simulation such as this. And then also expansion of scope. So we know kind of like the diagram on the right, we had started with a factory model, which is quite limited in scope. And it's something that we can then test very varying levels from this limited scope to something like the supply chain. So maybe you can include resource usage, you can include different aspects of that factory process, such as material receipt, dispatch, packing and dispatch and shipping. That gives you a more full picture of a factory process. And then also maybe it's multiple sites or a wider supply chain. And again, these are things that you can build on. And I think the kind of key point for us is, generally it's exciting to kind of be using and demonstrating the use of these tools and workflows within the construction industry. And basically what it means is that we can get kind of richer, more dynamic answers than previous modeling techniques that are used in the industry. So, again, we believe this is a core part of the construction industry in the future. So thank you. Okay, so just looking at questions. Is there some optimization in the model? So currently we don't have any optimization functionality in the model, but again, it's something that we're really interested in and pushing as part of the expanded kind of scope for these types of simulations. So, within the industry, as I mentioned, it's still not really widely used or widely adopted. And so what we're trying to do is we're trying to take projects like this and put in simulation and see where it works and see how it can help answer some questions. So there are definitely things that we could do in terms of optimization. So that could be a way of feedback for the production schedule. We know how many trusses you have to make, for example, for a particular type of building. And what you could do is you could have a feedback between some metric, some output that you're trying to optimize against. You could test lots of different production schedules and kind of make that smart to maybe reach an optimized, say, production schedule or some other factor. Do you think your case can be applied to address similar problems? So kind of take it as I think of meaning. I think, yeah, what we try, I guess, and do is that we generalize, or hope to generalize, kind of the approach, rather than make these specifics. So, with the something like AnyLogic and simulation, they're quite flexible, they're quite generic. And I think the learnings that we get and the way that we build the models, I think we can apply these, and we often reuse the way that we build models and the things that we do to different clients and to different sectors, and it's very similar to manufacturing. So I like to hope that there's a lot of transferability there. Okay, thank you,
David. Thank you very much for that. It's unfortunate that the video didn't work, but I'm sure later when we publish everything, the video will be available there, and so everybody will be able to see it and appreciate it.